Yeah, today is parent-teacher conferences, so I'll be here till 7:45 tonight. If your parent would like to come up and visit with any of the virtual teachers, we're here. We're up at the virtual building, and we'll be here forever. It feels like. Yeah. These these uh, these parent-teacher days are really long, especially when you get here at 7 in the morning, like I do. So most of these teachers don't get here till like 8:15, 8:30. So my day is a little longer. I get that break from like 2:45 to 4:15 because I'm really done with my day at 2:45, and parent teacher conference then start to 4:15. But there's really no need to go anywhere. I stay here usually and just try to get caught up on some grading or whatever we need to do. So I'll be here all day long. So I'm just looking at grades. Uh, Most people are doing really well. I have a few folks that's behind or getting behind a little bit. Um, Getting behind a little bit more than I would like because we got. I don't know if you realize what's left. So this is it for November. We're done because next week is Thanksgiving break, and when we come back, it'll be December. So this is the last week of November of school that we have. So it's like, okay, zoop, November's gone. When we get back, we have 2 weeks of classes plus finals week. That's it. 2 weeks of classes plus finals week when we get back. Fortunately, this is one of those classes you can be exempt from the final. So not everyone has to take the final. In here, you only have to take the final. If you have anything missing, you'll have to take the final. If you have a grade below 75%, you'll have to take the final. If you've had more than 4 absences or tardies, 4 absences, 4 tardies. If you've had more than that, you'll have to take the final. And if you've had more than 4 absences in your advisory class that ends at, if you have missed more than 4 advisory classes, you have to take all your finals. You can't exempt from any of them because that affects all your classes. But as long as you haven't had more than 4 absences in advisory, then I look at my requirements. No more than 4 absences, no more 4 tardies, no missing assignments, and 75% in the class. So that's coming faster than we realize. Like I said, we get back 2 weeks, then finals. Wow. So we're right on top of it. So that being said, if you're behind on assignments, uh, Thanksgiving week, maybe you may need to put in some time. Says you won't have any classes next week. Uh, I hate for people to have to use Thanksgiving break for schoolwork because I want you to have time away. I want you to spend time with family and friends and just relaxing and getting caught up on sleep and eating too much or whatever is on your agenda for Thanksgiving. But if you're behind some assignments, it may be that you've already taken part of your Thanksgiving break when you didn't do work before. So you got to pay that back by doing work during Thanksgiving break since you got behind on other stuff. Some of you may just need the time to get some work done. So uh, look in Buzz and make sure you scroll all the way down and see what am I missing? Am I missing anything? Am I current? Hopefully so. Great. But this Thanksgiving break is your last opportunity to really get caught up if you're way behind on anything. So I definitely want you to take a look at that over the break. The rest of this week, maybe Wednesday, Thursday, Friday, you can really pile it in and get caught up, so you don't have to use any Thanksgiving break. But it's coming. We are running out of semester for sure. So all right, glad to have you guys here today. We got to cover some stuff today. We're getting into logarithms. Oh, fun stuff. Logarithms. Let's get this up on our screen and see what exactly we're going to be dealing with this week. Going to our grade screen. Scrolling down, scrolling down, scrolling down. Wow, we finished 3 modules. We're on our 4th module. Look, we've got this week logarithmic functions and properties of logs. So that kind of goes together. Logarithmic functions, properties of logarithms. Next week, not next week, the next week of school, which is after Thanksgiving, we're going to solve exponential equations that have unequal bases. Because we looked last week at exponential functions like 3 to the x equals 3 to the 5th, x equals 5. But what if the bases are not equal? What do we do then? We'll look at that when we get back, along with graphing exponential, graphing logarithmic. And depending on how long this lesson is, I may move the 2 graphing lessons to be together A lot of times that works. Well, I'll take a look at that. So we may just do one lesson when we come back and then do two the following week because the graphing ones are usually a lot quicker. But this week we got to get to logarithms and properties of logarithms. So let's go take a look. Earthquakes and logarithms. Two things you wouldn't think go together. In the 1930s, so almost 100 years ago, at the California Institute of Technology, Charles Richter, you may have heard that name, Richter, developed the Richter scale, which describes the severity of earthquakes. When an earthquake strikes, a device known as a seismograph uses a needle that vibrates back and forth as the ground shakes. There's kind of a picture of one right there you can kind of see. The more the needle vibrates, the stronger the earthquake. So the distance of one needle vibration, from the top to the bottom, is known as the amplitude. So scientists take the logarithm of this amplitude, along with other measurements like the distance between the earthquake and where the machine is located, the seismograph, to determine the earthquake's measurement on the Richter scale. So logarithms are used when they tell, hey, this was a 6.5 earthquake in California. They took a logarithm as part of their calculations to get that number. So after this lesson, we're going to be able to answer these questions. How are exponential functions related to logarithmic functions? Because there is a correlation. How can a logarithmic function be created? And how can the properties of exponents help solve logarithmic equations? So I hope you got your notes from last week, the properties of exponents notes. We're going to add to that this week. We're going to have properties of logarithms. So let's go to page 2. Logarithmic functions. So suppose you were to graph the linear function 2x plus 3. Let's do that. Let's go ahead and go to demos here. And they wanted to graph 2x plus 3. Y, oh, it's still loading. How'd it go? Equals 2x plus 3. Okay, there's the line 2x plus 3. And it says, define the graph of the inverse function without doing all the algebra. You would reflect this across the line y equals x, right? So remember, an inverse function would reflect over. So if we have this point, 0, 3, the point 3, 0 would be on the inverse function. So the inverse function would end up being, let's see, what would it be? Y equals x minus 3 divided by 2. That's the inverse function. See, it's got the 0.30 where this has the 0.03. So any point that's over here, 1.5, 0, you can find its other point over here that's reflected across the y equals x. Right? And we learned that about inverses. And then you can verify it using algebra, so we're not going to worry about that. But the same process can be applied with the inverse of an exponential function. So let's look at the function. I'll leave that inverse line. Let's see, y equals 10 to the x. No, it didn't take it to the power of x. See, there's y equals 10 to the x. That red graph right there. So the same way, it's an exponential growth function. If we find the inverse of the function right there, that is the log. The log is the inverse of the exponential, equals log of x. Here, I'll make it red as well. See how those two are perfect reflections of each other over that y equals x line? This goes through 0, 1. This goes through 1, 0. Any point you can find on this one, you can find the opposite point here where the x and y are reversed. Exponential equations and logarithm equations, it's inverse operations. Inverse operations. So the logarithmic function is the inverse of an exponential. So the graph you see here is the most commonly used log function. So this right here is just log of x. just log of x. That would be the standard log of x equation. This is 10 to the x is pretty standard for an exponential equation. So, and let's see, logarithms like exponential functions do have bases other than 10, because we looked at, 3 to the x power and other bases. We can have other bases of logarithms as well. So the base of a logarithm is identical to the base of its inverse exponential function. So if you've got an inverse function of 3 to the x power, the inverse would be log base 3 of x. So you can have different bases on that. You can even have base e. E is equal to 2.71828. This is known as the natural log, and we write it ln of x. So natural log. But we're going to get more into that as we look through this lesson. We'll start our notes here in just a moment. But right here, a log function may be converted into an exponential function as this before. Let's write this down. Y equals b to the x. This is exponential that we looked at right last week. Exponential. Exponential equation, if we remember, has the variable as the exponent. And we can write this, as it shows in our lesson right here at the top of the page, right here. Log. The base is the base of the logarithm as well. So yeah, if you have a base of b, when you convert it, it's the base of the logarithm. So this is the exponential equation. This is the equivalent. Oh gosh, I didn't switch it back. Hold on. Hit the wrong one. This is the exponential equation. This is the equivalent logarithm equation. So the base of the exponent is the base of the log. The x up here, that is the exponent, goes on the other side for a log equation. So let's play just a little bit with this. Like if we said 8 equals 2 to the third power, right? That's exponential. That's, 2 to the third power. 2 times 2 times 2 is 8. As a logarithm, we would say log, the base is the base, log base 2 of 8 equals 3. So when you see a logarithm, that's basically saying, if I just have this part, I'm saying 2 raised to what power will equal 8? 2 raised to what power equals 8? Well, the answer is 3, because that's what it is, and that's exponential. 2 to the third power would equal 8. So this is how we convert back and forth. If we have an exponential or a logarithm, we can convert to the other form by making sure you just move the appropriate numbers into the appropriate positions. So that's our first notes is how to convert between logarithms and exponents. Make sure the base stays the base, and the rest of it kind of falls in place there. All right. So they give an example here of log base 8 of 512. So log 8 of 512 equals what? So it's basically asking 8 to what power would equal 512. So you can rewrite that as an exponential equation. Y equals 8 to the x power. And since we know it was 512 is what the y was, we're saying 512 equals 8 to the x power. Well, 8 to the third power is 512. So you have 8 to the third equals 8 to the x, which means 3 equals x, because we learned that with our exponential properties. If you have the same base, set the exponents equal to each other, x equals 3. So that means 3 equals log 8, 512. because 8 to the third power would equal to 512. Important note, if you're given log 3, 9 equals 2, 3 is called the base. 9 is called the argument. And 2 is the exponent. Because this is 3 squared equals 9. If it's written as an exponential equation, 3 squared equals 9. 3 is the base, 2 is the exponent, 9 is the argument. We use the same terms in both logarithm and exponential. They're just in a different order. Base, argument, exponent, base, exponent, argument. But argument is the number that we use after the log for whatever base it is using. So now I want us to look about creating logarithmic functions. So it says, let's start with some numbers. Okay, so we can do this. X and f of x. And it had f of x being 1, 2, 3, 4. Yep. 1, 2, 3, 4. And the f of x, the x they use is 2, 4, 8, 16. Okay, 2, 4, 8, 16. So this is kind of backwards to what we were doing with exponential, because exponentials we had 1, 2, 3, 4 as the x. And we saw that the f of x, what it equaled, was going up times 2. But in this case, we see this going up times 2. Yep, times 2. Where this is just going up 1. Plus 1, plus 1. Right, so looking at that then, plus 1, plus 2, plus 4, plus 8, which is times 2, times 2, times 2. So this means this is a logarithmic function where f of x equals log 2 of x. Log 2 of x. So let's check some of this. So it says 2 is 1. The answer to 2 is 1. 4 is 2. 8 is 3. So this says log 2 of the x is 2 equals 1. The f of x would equal 1. So if we wrote this as an exponent, that means 2 to the first power equals 2. Yeah, that's right. Yeah, 2 to the first power is 2. So log 2 of 2 would equal 1. If it's 4, log base 2 of 4. 2 taken to what power is 4? That'd be 2, right? 2 squared equals 4. Well, 4 does equal 2. Let's look at 8. Log base 2, and the argument is 8. So this is the same as 2 to what power equals 8? Well, 2 to the third power equals 8. 2 times 2 times 2. So that means the exponent would be 3. Well, when it's 8, it is 3. So we're seeing as we check all of these, the log base 2 of 16 is 4, because it's 2 times 2 times 2 times 2 would equal 16. This is what the table would look like to tell us this is base 2 log function. Base 2. If these were times 3 times 3 times 3, then we're like, oh, this is log base 3. It just tells you what the base is going with that table. So they talk about that here. Check to make sure it works. It says log 2 of x. So they go to the same thing, log 2 of 2, or f of 2, if they put x in, and it equals 2. 4. So 1, 2, 3, 4 is what it equals for the 2, 4, 8, 16. It says, okay, let's see what this is. Example 2. So now we're going to figure out one that they do a little differently. So I'll write this down and switch over. Again, let's see what's going on. This is going up plus 1, plus 1. So this is consistent. 16 to 64. 16 times 4 is 64. 64 times 4 is 256. So this must be f of x equals log base 4 of x. So if x is 16, log base 4 of 16, our f of x should equal 2, right? Should be f of 2. And it is. 4 squared is 16. 4 squared, because that's what the base times whatever number over here. Log base 4 of 64. The x would be 3. 4 to the third power is 64. 4 times 4 times 4. So this is log base 4 of x. So I said, look how the values increase. It's times 4. It's plus 1. So this is log 4 of x. And then they check the numbers as well to get into there. F of 16 is 2, 3, and 4. Okay, let's look at page 4. Logarithmic functions. Okay, we're going to learn how to evaluate this log 5 of 1 over 625. So we got a couple of videos. We got 2 examples here. They're both with videos. So let me switch over where we can hear the sound.
To evaluate log base 5 of 1 over 625, first, write the expression in exponential form. This expression is not equal to a number, so set it equal to the variable x. Rewrite the logarithmic equation as an exponential equation with a base of 5 raised to the power of x, which equals 1 over 625. Notice that the original equation is in the form base number exponent, BNE. Its equivalent exponential equation is in the form base exponent number, BEN. Now, solve for the variable. To find a value for x, the bases on either side of the equal sign must be identical. 625 can be written as 5 to the 4th power. Indicate an exponent in the denominator of a fraction using a negative exponent. Once the bases are equal, cancel both to find the value of the variable. Now, check your work. Set the original expression equal to the solution. Rewrite the logarithmic equation as an exponential equation and simplify. The solution is verified.
Okay, this goes back to last week. Using our properties of exponents, we had that negative exponent property, where if you have 1 over a number, it's the same as x to the negative exponent. Like 1 over x to the m is the same as x to the negative. So they had 1 over 625. 625 is 5 to the 4th. So that would be equal to 5 to the negative 4th. So that's how they set that equal to each other, by converting these to both base 5. So 5 to the 4th to solve. So that's what we need last week's notes. What do we do with the product property, the quotient property, power property, and the negative exponents? Because we'll use that again this week in solving logarithms. That's why we know how to convert back and forth between them so we can use our exponent properties. All right, we have another video here for another example. Let's take a look at this. This is going to solve Ln. Now let's talk about this real quick. Let's put that on our notes. Yep. All right, let me review this. If we have logarithm of x, and we just write like that, doesn't have a base. Here we had base 2. Here we had base b. This is assumed to be base 10 then. We don't have to write that. We don't have to write that at all. Just like if we write x equals 4, this is x to the 1st power. We don't write the 1 because it's just assumed. We know that's x to the 1st power. So we don't write the 1. That's not needed. Like here, we don't have to write base 10. That's just assumed. It's not needed. When we have a square root, we don't write the little 2. It's assumed that there's a 2 there. We don't have to write that. Likewise, if we have ln of x, this is log base e of x. The base is e. You're like, what do you mean it's e? Well, if you remember, e is a number. We can find it on our calculator. It's right here on my calculator. E equals 2.71828, blah, 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 blah. E is a number. And so on your calculators, you will find a log button and an ln button. Ln button is base e. If you write ln, it's like writing log base e. You just don't have to write the e if we use ln. It's called the natural log. Natural log. So these are just assumed cases. When you do that, that is base e. When you do that, that's base 10. So those are some things we just need to understand. Remember that if you don't put a base, it's assumed to be 10. And if you use ln, it's assumed to be e, which is used in certain cases. And we'll look more at that. So, all right, let's go back to the video we were needing to see next. If I can find where I've got that hidden on my screen now. Ah, here we go. All right. All right, and this one's using the natural log. So you'll get to see it in action here.
To solve the natural log of x equals 3, first rewrite the natural logarithm in exponential form. Remember, the natural logarithm represents a logarithm with base e. The next step is to solve for the variable. Using your calculator, find the value of e cubed. The final step is to check your work. Substitute 20.09 into the original equation to verify the solution. Using your calculator, find the value of the natural logarithm 20.09. The solution has been verified.
So if we use our calculator, they were talking about you could take e and raise it to the third power. I use this x raised to the y power button. So if I do that, it says e to the third power equals 20.0855, which is what they had, or they rounded it to the nearest hundredth, 20.09. So it says if you want to check that to see if the ln of 20.09 does equal 3, if we go here and we're going to round it, so it may not be exactly 20.09, and we hit the ln button, it's 3.00022 because we rounded. So it is ln of 3. So that ln is base e, and you would use that e button on your calculator. You need to calculate something on that. So just showing you how that works. We don't often do natural log, but when you see a natural log problem, don't freak out. It just means it's base e, which is a number. We don't use e very often. So it says solve log b81 equals 2. All right, we'll put that down and just log b. And so the way we solve that is we have to rewrite it as an exponent because we've got all those exponent properties we can use. So b is still the base. That is our exponent, and it equals 81. So if we want to find what the base is, take the square root of each side. So instead of b squared, it's just b, and this is 9. Now, there is, when you take the square roots plus or minus, but we don't have negative bases. So we just take the positive. So it's base 9. So log base 9 of 81 equals 2. So 9 squared equals 81. So we just rewrite it as an exponential equation. B squared equals 81. So if B squared is 81, what's B? It's 9. So we can solve exponential equations that way. Rewrite in exponential form. Oh, it says rewrite it. What is the base of the equation? B is the base of the equation. Great job. Oh, and there's a little next hidden down here. What power will it be raised? It will be raised to the power of 2. Great. It says what number will it equal? It will equal 81. Great job. And then step 2, how do you find the value? We set the square root of each side. It's plus or minus 9. It says check your work. Oh, will it let us do that? Oh, no. So substitute both 9 and negative 9 into the original equation to verify. So log 9 of 81 equals 2. So 9 squared equals 81. The solution of 9 is accurate, but what about the negative 9? Log base negative 9 of 81 equals 2. When negative 9 is substituted, the base of the logarithm is negative. Neither the base of a logarithm nor the base of an exponential equation may be negative. So again, we throw it out like we don't have in exponential equations. We don't put a base as a negative. We don't put a base in a logarithm as negative either. So throw out the negatives. All right, here's the lesson summary. So we're going to look at the next lesson here in just a moment. There is another example, by the way, if you want to look at another one on solving. If you want more practice on that, they do have, well, it's not even loading. Hello. There it is. They have another one you can try. X minus the log base x minus 4 of 36 equal 2. So that one's got a little bit more fun in there because you got to square that. But let's look at the lesson summary. It goes through the stuff we've learned. To solve a logarithmic equation or evaluate a logarithmic expression, here's the steps. Rewrite it as an exponent. Solve for the variable. Check your work because we can solve exponents. Logarithmic function is the inverse of an exponential function. It can be written y equals log bx, where y is the power, b is the base, x is the argument. Logarithms are base 10 are written without the base, like we just said, log of x. It's assumed to be a 10. And log's base e, we just write as ln, natural log. Because e is called the natural number, so natural log. And then the conversion, knowing how to convert between them. Y equals b to the x is the same as x equals log base b to the y. Okay, that is that. We do have some practice problems you can look at and attempt to make sure you understand logarithms, because we don't work with logarithms very often. Evaluate each expression. Log 3 of 243 equals what? So 3 to what power would be 243? If you rewrite that, 3 to the x equals 243. So what power? Well, 3 times 3 is 3 squared. That'd be 9. Another 3 would be 27. Another 3 would be 81. Another 3 would be 243. So that's to the 5th power. So log 3 of 243 would be 5. Now, I will show you, you're like, well, I have a calculator. Can I do the log on there? Most calculators, simple calculators, I can't say log base 3. All I can say is log 10. And log 10 of 243 would be a totally different answer because it'd be 10 to the power of 2.38. Does not have a different base. Some of them do, but in our next lesson, we're going to see how we can cheat and use a plain calculator to solve different bases. Not really cheating, but it's a pretty cool method. So anyway, you can figure it. Log 4 of 1 over 256. That's one of those where you got to convert to a negative exponent and set it equal to each other. All right. More practice problems on page 6. This is log b of 1,000 equals 3. So what is the base? What number taken to the 3rd power would equal 1,000? Again, you just rewrite them. And we know, oh, that'd be 10. 10 to the 3rd power is 1,000. Shows you how to rewrite it, how to solve it. And there's 4 problems there. X plus 2 is the base. To the 3rd power equals 27. All right, let's go look at the assignment that goes with this first lesson. Which log function represents the data in the table? So this is log what? Which one of these? Evaluate this. Log 4 of 16. Which one of those would that be? Log base 4 of 16. Log base 2 of 1 over 64. Here's log base x plus 5 of 36 equals 2. And solve log x equals 3. So what is the x? That's base 10. Don't forget, that means 10 to the third power. All right, we'll leave this. Let's look at our second lesson on properties of logarithms, which means we're going to want some more notes here, because we're going to learn properties of logarithms. Uses of logarithms with different bases. So a logarithm with a base of 2 is used in computer science because it connects with the binary numeral system. And since computers run on binary, it uses base 2 for a lot of different things. So a logarithm of base e is used with interest rates to determine when a specific amount of growth has occurred. Remember, we had that continuous interest formula that used PERT? Well, we can rewrite that as a logarithm using that base e. So a log with base e is called a natural log, and abbreviated as LN. We just looked at that. A log with a base 10, like the one used in the Richter scale, is called the common logarithm. And on a calculator, the button has log on it is the common logarithm, which is base 10. So you have the common log and the natural log that you don't have to write a base with. We're going to learn to answer this. How can the properties of logarithms be applied to simplify or solve equations? And the base change property can help in what scenarios? Oh, you're going to love the change of base property. This is a good one. We're starting right off with the change of base formula. Not all logarithms are in base 10, base 2, or base e. It's helpful how to know how to change different bases into one that you can use on your calculator. So it's in the logarithm expression, log base 2 of 8. The small 2 in the corner of log is called the base, and the 8 is the argument. Right? So we can rewrite that as 2 to the x power equals 8, and we can solve it to know x equals 3. But what if we wanted to do that with a calculator? This one's a pretty simple one, right? 2 to what power equals 3, but they're not all going to be that simple. So it says, let's try calculator to see what we can do with the log 2/8. So I'm going to put this in our notes. They got it as experimenting to figure it out, but we're gonna put this in our notes. I'm going to give it to you right away for the interest of time here. So if we have log, and I'm going to use base, I'm just going to give a variable, x of y. All right, and we're trying to solve this. Now, it would have numbers normally. With our calculator, we don't have base whatever x is, unless it's 10 or e, right? We don't have that in our calculator. We can rewrite this. This is called change of base. Let me write this over here. Change of base. We can rewrite this as log of y divided by log of x. This is base x. What base am I using over here? It's base 10. I didn't write anything, right? If I don't write a number as the base, this is assumed to be base 10. So going back to the example they just gave us, if we have log 2 of 8, that's the same thing as log of 8 divided by log of 2, which we know the answer, 2 to what power equals 8. We know the answer should be 3. But what does our calculator do when we try to do that? So let's do this with a simple one that we know, right? Let's take log 8, let's clear all that, and divide it by log 2. So I think with this calculator, I have to hit the 8 first. Yeah, invalid input. Some of them you hit log first and then the number you want to take the log of. This one I have, you got to hit the 8 and say, I want the log of 8. So that's the log of 8. And I'm going to divide it by the log of 2. 3. Dividing the log of 8 by the log of 2 gives me the correct answer that I had over here as log base 2. You're like, that's pretty cool, but I could have also done the natural log of 8 divided by the natural log of 2. As long as I use the same base, it doesn't matter. 8 natural log is 2.079 divided by 2 natural log is 3. Oh, that's cool. You can use one of these plain logarithm buttons right here on your calculator to solve any base. I solved log base 2 of 8 with just my plain calculator buttons, just my log buttons. And you can use log of 8 or the natural log of 8, either one, and use, this is the change of base formula. Change of base formula. So this is a great one to have in your notes, change of base. And it works like this. The y goes up here, the x goes down here. As long as you know which one to put where. That's why it's great to have an example. This is great, but make sure you write down an example to go with it so you can see with numbers exactly how to do that, so you can put it in your calculator and solve. We didn't have to rewrite that as an exponent. We could, we can write 2 to the x equals 8, but we can just find an answer in our calculator with the change of base formula. Oh, that's sweet, Mr. Brock. Less work, just punch up my calculator. I love it when my calculator gives me the answer. Well, it will if you know what to put in your calculator. That's the key, knowing what you put in your calculator. So it shows this, the change of base formula right there. And they use B, and that's probably a good one to use because it's base. The base goes on the bottom. Log B goes on the bottom. Whatever the base number is goes on the bottom. Whatever the argument is goes on the top. Log Y divided by log B. So the change of base formula allows you to find the value of a logarithm with a base other than 10. Calculate. See, divide the common log. So there it is, log 8 divided by log 2, and it'll give you that 3. And as I talked about, you could do it with the natural logum as well. So let's see. Oh, what's it saying? Evaluate natural log of 9 round to, okay, this is just using a calculator to solve just plain problems here. So here, I'm gonna close that and reopen it to get rid of all that extra stuff we got going on now. Okay, evaluate logarithm of 9, natural log of 9. So 9 natural log, 2.197 to the nearest thousandth. So yeah, 7 would round down, 2.197, 2.197, that's the nearest thousandth. Great job. So just making sure you know how to do that. If you want to check, make sure you get the right answer. Make sure you know how to use the calculator you have on your computer. Or there's a calculator usually up here that I've turned on. If I haven't, remind me. So it says if we use the change of base formula of the natural log of 9, you can take the natural log of 9 divided by the natural log of e, because that's what the base is. It'll give you 2.197 as well. We could have done the log base 10. So if we went and said log of 9 divided by the log of e is 2.78 divided by that, I should still get that 2.197. I still get the same answer. Just using the change of base formula, using them as base 10. Just using 9 and e as the numbers. So this is another example, log base 27 of 81. And they're using base 3. Log base 3 of 81 divided by log base 3 of 27. You can, as long as the same base on the top and bottom. We like using 10 because it's on our calculator. Now this calculator actually does let me choose different bases. If I shift it, I can do log, let's see, 81 base 3 divided by 27, shift this base 3. That's 1.33333. So if you take 27 to the 1.333 power, you'll get 81. Oh, what do they got there? Oh, this is log 4 of 4. Oh, that's a good one to think about. Log 4 of 4. If you take log, let's say the base and the argument are the same number, it's always going to be 1 if these are the same number. Because if you rewrite that, you're saying 4, oh, not x. 4 to what power equals 4? 4 to what power equals 4? Well, x is going to be 1. This is 4 to the first power. We don't write that, but x equals 1. So anything where the base and the argument are the same is 1. Always. Always, always, always. So if you want to try that, in your calculator, say, okay, what about log of base 10? Base 10 of 10. Well, that's 1. How about if I do the natural log of e? The natural log of e is 1 because it's base e of e. Yeah, e to the first power equals e. So, yeah, some of these are like, yeah, that's pretty obvious. 4 to the first power would equal 4 to the first power. There is a little bit of the duh property here. Duh. Here's some more examples for the chains of base formula. For the common log, find log 7 of 15, round to the nearest hundred. Doesn't give me where to type that. It's just showing me the steps, I guess. Step 2, so you take log 15, divide by log 7, and it equals 1.39, because the log of 15 is 1.17, the log of 7 is 0.84, and equals that was divided. So just give you some more examples if you need to look at some. Log 49 of 343, rewrite that as a logarithm of base 7. Okay, that might be worth our watching, because this is saying, how can we rewrite this as a base 7? And that's going to use some of our exponential properties as well, I believe. So let's take a look at that. It's kind of hidden down there in example 3, but worth the time.
According to the change of base formula, you can divide the log of the argument, 343, by the log of the base, 49.
And put them both as base 7.
Use base 7 for each log.
So they're using base 7 because 49 is 7 squared. 343 is 7 to the third power. And so this would end up 3 divided by 2. It's 1.5. That's 1.5, because if you simplify those, it gives you a nice, easy numbers to work with. So, all right, we'll go to page 3 here. See what surprises that holds for us. All right, we're going to get into more properties here. So let me make sure I'm sharing this properly to go to our notes. We've already got the change of base property there. Let's add some more properties. So we've got the change of base. That's the first one, where you can take these and use any calculator. Let's see, what's our next one I need to go over? The equality property. Okay, the equality property with logarithms. And this one is very much a kind of a, well, duh type thing. If we have, let me see, I'm going to put log base b of x equals log base b of y. These have the same base, right? Log base b. Then if log base b of x equals log base b of y, here it is, x equals y. It's like, seriously, Mr. Brock? Yes, seriously. Because think about that. If we have a log base 5 of 125, that would equal log base 5 of what? Pretty sure x is going to equal 125. Log 5 of 125 has to equal log 5 of 125. It wouldn't equal any other argument. So yes, this is kind of one of those. It's like, well, duh. As long as these have the same base. So don't miss something that simple. If they have the same base, it's kind of like our 3 to the x equals 3 to the 5th. X equals 5, right? Same base. These have to be the same for these to be equal. Equality property. Let's see. Let's do the product property. There's a product property for this as well. We had one for exponentials. And the product property for logarithms is pretty simple as well. Let's see. If we have log b of x, and we are adding it to log b of y, that is going to be equal to log b, the base is going to stay the same, of xy. So let's put a practical example over here. If we have log base 4 of 3, let's say, plus log base 4 of 5, that equals log base 4 of 15. Now that twisted there. That's how that works. If we have log base 4 of 3 plus log base 4 of 5, we can multiply the 3 times the 5 and get log base 4 of 15. We could do that with any base. If we did log base 10, we can check it with our calculator real easy with the log base 10. So let's say we have log base 10 of 3. So there's the log of 3. It's 4.77. And we're going to add to that the log of 5. So it equals 1.17. So this is saying that would be the same as the log of 15. Which is, oh, I hit twice. Log of 15. Look, that's also 1.176. 1.176. Just like it was when I added log 3 and log 5 together, I got 1.176. If I just take the log of 15, it's 1.176. It is equal. That is the product property. So let's look at the quotient property then. Quotient property works much like exponential does. Log b of x minus log b of y would equal log b of x divided by y. X divided by y. So if we have log base, let's say 7 this time, of 54 minus log base 7 of 6, that would be the same as log base 7 of 9, because I took 54 and divided it by 6. 54 divided by 6 is 9. Divide x by y. I'll write that down there. 54 divided by 6 equals 9. So it equals log base 7 of 9. Important thing is keep the same base. The base stays the same. Base stays, and the base has to be the same for this to work. If this is log base 2 of x plus log base 3 of y, I can't do this. The base has to be the same. That's part of the trick there. Quotient property. Let's see. Oh, this was the big one that's used a lot. There is a power property. It's interesting, isn't it? This is the exponential notes we took last time. We had a product property, we had a quotient property, we had a power property. We're just going down the list. Same properties, they just work different for logarithms, just a little bit. Let's see, what's the best way to do this? If we have, I'm going to say this, y times log b to the x power, we can rewrite that as log b to the power x to the power of y. The argument becomes this. And it works both directions. That's the thing about it. So if we have 4 times log 7 of 3, that's the same as log 7 of 3 to the 4th power, or log 7 of 3 times 3 times 3 times 3, log of 7 of 81. So you have a number out front, it becomes the exponent. This becomes the exponent. This goes right up here. Like that. So the 4 becomes the exponent of the argument. The base always, again, the base stays the same. We didn't change the base. But now 3 to the 4th is just 81. 3 times 3 times 3 times 3. That is the power property. Okay. Let's go back and see if there's something we missed that they're talking about on our notes. There's our product property, our quotient property, and our power property. And they do have this in our lesson. So let's go back and see how the lesson presents this. This was the how to convert back and forth properties of logarithms, rewriting it as an exponential. We have that in our notes. We had that. The equality property, yeah, that's the first one we wrote up there, where log b of x equals log b of y, so x has to equal y. Right? Think of it like canceling out log b from both sides, or log 4 from both sides. The product property we just looked at, if we have log 7 of 3 plus log 7 of 5, that's log 7 of 15. You take 3 times 5. They have the same base, and it's being added. So 3 times 5. So if 2 or more log expressions with the same base are added, you just multiply the arguments. Called the product property of logarithms. So log bx, log by equals log bxy. That's how we had it written. There. Oh, here's a proof. Remember proofs from geometry? We have proofs for everything in mathematics. I want to see how the proof works. So they put log b of x, log by equals m. Then they create 2 equations, one showing the x variables being isolated, the other one showing the y is isolated. So they solved it for log x. They basically subtracted log b of y on this one. On this one, they subtracted log b of x. Then they rewrote it as an exponent. B raised to the power of m minus log b of y equals x. Wow, that's complicated. Over here, just the opposite. And then combine the two equations in one by multiplying the left sides of each equation and multiplying the right one. So if this equals this and this equals this, if we multiply this times this, then we can multiply this by this on the other side, since they're equal. So then, since they have the same base, they add these terms. So you got 2m. This is great. Factor of -1. To where this is a minus and a minus. Now it's a minus parentheses plus. Proofs are always fascinating because it's amazing how much work it takes just to prove something's true. Then you substitute m. Since this is the same as m, which was defined way up here, it said that's what m equals. We can just substitute that for m. So now b to the 2m minus m equals xy. So b to the m power, because 2m minus m is m. Rewrite that. You got log b xy equals m, which is proven right there when you substitute back for the m. All right. I'm not making you write any proofs, so you don't have to study this. I just wanted to look at it to see how that's proven. It is crazy. Now put this in action. So that takes log 8 of 5 plus log 8 of g plus log 8 of 4. So in this case, we have 3 logarithms with the same base being added together. And since they're being added, it means you can multiply them all. 5 times g times 4, or log 8 of 20g. That's as simplified as it gets because we don't know what g equals. So yeah, that property applies even if you have 3 things being added together. As long as they have the same base, you just multiply the 3 arguments. Here's another example. Oh, let's look at this example because it uses a lot more stuff in here than we've been working with our examples. So I'm going to put this one up.
To solve this equation, first confirm that each logarithm within the equation has the same base. Since all bases are the same, simplify this equation using the product property of logarithms. Multiply the arguments 6 and x minus 3. According to the property equality for logarithmic functions, when identical logs are isolated on either side of the equation, those logs can be eliminated. Now, the equation looks like 1,000 other equations you have solved. The solution is x equals 7. Now, check your work. Substitute 7 into the original equation. Then simplify. The solution is confirmed.
There you go. I like that. So it looks pretty complicated at the beginning, but using our product property, since these have the same base, we can multiply 6 times x minus 3. And then, since we've got log 4 of something equals log 4 of something, we know those two somethings have to equal each other. That was the kind of the duh property I said. So we can just set them equal to each other. 6x minus 3 has to equal 24 because that's what the two arguments are for the same base logarithm. Then it's just a matter of solving that. So that's pretty nice. I like that. Now here's the quotient property that we looked at. Log 7 of 40 minus log 7 of 8. You can just take 40 and divide it by 8 and you get 5. Okay, so they have some examples of that as well. Log 3, 4 minus log 3n plus log 3, 2. So you got a couple of things going on. First, you can subtract the logs, which means you divide 4 by n, you get 4n. And it's being added to a log, so we can combine and use the product property as well and multiply 2 times 4 over n. So we get 8 over n. So it's combining the quotient property and the product property to simplify it to log 3 of 8 over n. And they got more examples here, and they have another example hidden here. So if you're struggling to understand the quotient property, we've got plenty of examples of that. Let's look at page 4. The power property, we've got that in our notes as well already. Log 7 of 2 to the third power can be written as 3 times log 7 of 2, right? Or the other way. We have it in our notes the other way, where if we started with 3 log 7 of 2, we could rewrite it as 7 log base 7 of 2 to the third, which would be log base 7 of 8. But we can go whichever way we need to if we're trying to simplify the problem. So the exponent 3 on the argument 2 becomes a coefficient. We can go vice versa, either way. You can confirm this fact by using the change of base formula. So log 7 of 2 to the third is 3 times log 7 of 2. And if we use the left side, change of base would be log 8 divided by log 7. The right side would be log 3 times the log of 2 divided by the log of 7. You put those in your calculator, they both equal 1.068621. They are equivalent. It is the same thing. So they show the power property here. Log b of x to the y is the same as y times the log b of x. Oh, and there's another proof, but we won't go through all of that. I may come look at it later. But there's a proof on how that has worked. And there's a proof of the change of base formula as well. So, all right, fun stuff. So here's an example that does a lot. Look, we've got all of this going on. So let's see if we can put this one in our notes and work through that. Okay, so they want us to simplify this. So the first thing I want to check is to make sure everything is the same base. And they are. They're all base 5. Since they're all base 5, then all of these properties that I have in my notes should apply. I can use any of these properties. The power, the quotient, the product, all that stuff. So I'm going to rewrite these, starting with the ones that have coefficients. So I'm going to write this as log base 5 of x to the third power. So I took this and I moved it to be the exponent. To rewrite that, x to the third power. This I'm going to leave like it is for the moment, log base 5 of 2. But here's another one that I need to rewrite as an exponent. So this is minus log 5 to the y to the fourth power minus log 5, 9. Okay, so now, since I've used the power property to rewrite these, let's start using the product property right here. So that means I can take these two, since they're being added together, and I can multiply the arguments. They're both the same base, so this is log base 5 of 2x to the third. Because 2 times x to the third. Minus log, I'm going to do this one step at a time, y to the fourth minus log 5 of 9. So now I'm going to take the next two. This is subtracting. This is the quotient property. So this would be log base 5 of 2x to the third divided by y fourth. Since these are the same base being subtracted, I take the first one and I divide it by the second one. I'm doing this one step at a time. You could combine some of these steps. Now I have this being divided by that as well, since that's being subtracted. So it ends up log, we still have the 2x, base 5, 2x to the third on top. But now it's also, not only is it being divided by y to the fourth, the other's a coefficient. I should put it in front. It's going to be 9y to the fourth, because we have a 9 that we're also dividing by. So taking it step by step, the first thing we did was the power property to rewrite both of those as exponents instead of coefficients. Then we used the product property to multiply those together. And then these are both subtracted, so we divided by both of those. I did them one at a time, but it simplifies to log base 5. I still have that same base, follows all the way through, of 2x to the third, 9y to the fourth. Simplify. Start as a really long problem. We got it down to just one base 5 expression. Let's take a look at what they got. 2x to the third, 9y to the fourth. Log base 5. Exactly what they got right there. Here's another example if you need to look at that. And here they want to review rational exponents because of the next example right here. So if you look at rational exponents review, remember if we have t to the 3/4 is the fourth root of t to the third. We have the eighth root of w to the fifth. That's the same as w to the 5/8. That we'll review on those radical exponents. Because with this, we've got exponents that are going to be fractions. So when you simplify that and rewrite those, you've got 216 to the 1/3 power, which rewrites as the third root of 216. And this is, we probably should put this one in our notes as well, just to have an example of one that's a bit more complicated, but not too bad. So this one, they want us to actually solve what is n equals. So that's what we're trying to do. Find out what does n equal. We have an n over here. So if, again, the first thing I want to check, I'm dealing with the same base all the way across. They're all base 9. I'm going to rewrite this, make it an exponent, both of those, using the power property. So this is log base 9 of 216 to the 1/3 power plus log base 9 of 64 to the 1/2 power equals log 9 of n. So this can be written as log base 9 to the 1/3 power can be written as the third root of 216. And here the log for 9th power to the 1/2 power means it's the square root of 64. And it all equals log 9 of n. So here's what we can simplify this way. What is the third root of 216? That's actually just a nice number. So we have a log base 9. 6 times 6 is 36. 36 times 6 is 218. So the third root of 216 is just 6. Because 6 times 6 times 6 equals 216. And over here, we've got log base 9. The square root of 64 is 8. That's log 9 of n. Now what have we got? We've got these being added with the same base. So this is log 9 of 48. Remember, we multiply. Product property says 6 times 8. Equals log 9 of n. Now we've got that equality property. Log base 9 of 48 has to equal log base 9 of 48. Means n has to be 48. Because there's no other number that would work. Log base 9 of 48 is log base 9 of 48. So that gets back to having to do those radicals and exponents and converting between those two. We never leave anything behind in math. We drag it along forward to the new lessons. So even though it's been a while since we've looked at radicals and exponents, we still have to keep that in our tool bag so we can pull it out and use it in times like this. All right, we've got a few minutes left. We're almost done with the lesson. Log 948 equal that. So solving it, n equals 48. All right, page 5. Yes, there is 10 pages of this one, but this is the last page because there's the lesson summary right here at the bottom. The rest are all practice problems. Solving logarithm equations with constants, like log 7x equals 3. The 3 on the right side is not a logarithm, but we know we can just convert that, and this is 7 to the third power equals x. So it's 343. So it says, let's solve something like this. All right, so let me turn our paper over, write this one down. So they're basically combining like terms. So this is not in parentheses. If this was in parentheses, the argument would be x minus 1, but it's not. This is just log 4 of x minus 1 and log 4 of 2 plus 1. If this would be different if that was in parentheses, but it is not in parentheses. So this is not part of the logarithm. That's not part of the logarithm. So we got to add 1 to put that over here. So this is log base 4 of x equals log base 4 of 2 plus 2. Again, this is not in parentheses, so this is not part of the logarithm. Now we can move this to the other side. Subtract log 4 of 2. So over here we have log 4 of x minus log 4 of 2 equals 2. Quotient property, right? Quotient property says, hey, we're subtracting 2 logs with the same base, so that means I divide. So this is log 4 of x over 2 equals 2. Great. Now I've got just a log equals something, so I can rewrite this as exponent. 4 squared equals x divided by 2. Right? That goes back to our very beginning notes when we said, how do we change from a logarithm to an exponent? I take the base, make it the base. I take the exponent, make it the exponent, and the argument over here. So I took this. The base is still the base. 2 is the exponent. This is what it equals. So this is 16 equals x divided by 2. So I multiply both sides by 2. 32 equals x. So now we have to check that. So if we have log base 4 of 32 minus 1, does that equal log base 4 of 2 plus 1? Good question. Let's just check it with our calculator. We can make both of those a number and see if they're the same number. It's one way we can do it. I mean, we can do the algebra to make those equal the same thing, or we can just check it. Log 4 of 32. So that means I can check. I just want to use my change of base. And over here, I can do log 2 divided by log 4 plus 1. So let's see what log 32 divided by log 4 minus 1 equals. So 32 log divided by 4 log minus 1. So this equals 1.5 on this side. So let's do log 2 divided by log 4 and add 1. Oh, this equals 1.5. It works. It is 32. X does equal 32 because we checked it with our calculator, found out this It's 2.5, and you subtract 1 is 1.5. This is 0.5, and we add 1, we get 1.5. So they work through the same thing. They simplify that to log 4 of x over 2 equals 2. They rewrite it as 4 squared equals x divided by 2 to get x equals 32. And see what they do when they checked it. They went ahead and rewrote everything and did the algebraic form to get it to 4 squared equals 16 and 16 equals 16. We confirmed it another way. All right, let's look at, there's more examples on how to solve with just like a constant and different constraints on that. So more examples that you can look at, but let's look at the lesson summary because we're about out of time. Has the change of base formula, has the equality property, the product property, the quotient property, the power property, and how to rewrite things with a constant, like log 7 of x equals 3. So that's 7 to the third equals x, or 343 is what x is. That was the first thing we wrote down, was how to go back and forth between exponents and a logarithm. But you got to have just one constant on the side. You can't have logs on both sides. But there's the main things you need in your notes. If you had this page printed out or this copied down, that would help you a lot. There are several pages of practice problems for you to make sure you understand this before we end up testing on this later. Evaluate the expressions in nearest hundred. Log 4 of 8. Use your calculator. Do log 8 divided by log 4. See what it equals. There are 3 problems there. The next page. Practice. Write log 215 as a logarithm of base 8. Change the base formula. So if they both had base 8, we could say log 15 and log 2. Those are the same. Log 8 of 15 divided by log 8 of 2 using change of base formula. Yeah. We just usually do log base of 10, so we can put it in our calculator, but you can change it to any other base. Right as a base of 6. Both those base 6. All right, page 8. More practice problems. You try 1, 2, and 3. What is the correct simplification of this? Log 6 of x plus log 6 of 8 plus log 6 of 5. So basically, it's going to multiply those together. 3 problems. Then there's some more problems here. Simplify this. You got these being added and these being subtracted. What do you end up with? Is there more? Oh, there's more. I don't know how many more, but there's more there. And here, answer to see if you're correct on simplifying these. And there's more problems there. It's hidden down there. All right, page 9, more practice problems. They give you plenty of practice because there's a lot of properties that we learned in this lesson. A lot of properties. Log, this you're solving. What does x equal? Log 5 of x plus log 5 of 2 equals 1. So you can solve that. I think it's like that one. Oh, no, that wasn't it. I assumed something. Try that. Here's gives you the solution. And again, there's more down here. Let's go look at the assignment before we're totally out of time. Start. Evaluate log 3 of 9, which means 3 to what power is 9? Oh, I got that one. Log 8 of 12. That's not going to be a nice number. Evaluate the natural log of 7. That's just in a calculator. You just pull up the calculator. Do I have the calculator? Yes, I do have the calculator. This one, I think you hit the button first. Natural log of 7. So you hit, oh, got the answer. So it does have to hit the natural log first. Write log 3 of 6 as a logarithm base 2. So which number goes on top, basically? Write this as a base 5. Solve this. Oh, it looks like we got 10 problems this week. 10 problems. I need to make sure this is worth enough points for 10 problems. All right, guys. Like I said, this is it for November. Once you get this done, as long as you don't have any missing assignments going backwards, all we have left is 2 weeks and then finals week when we get back. So this is due Sunday night, but next week's Thanksgiving. So guess who's not going to be grading this next week? Yeah, I'm not going to look at it until December because that's the day we get back. It's December 1st. So this is due Sunday, but I'm not looking at it until December 1st. So have a great Thanksgiving break. If I don't see you again, this is a B-Day Friday. So I'll be here Thursday and Friday if you need any help with anything. Otherwise, we'll see you in December, guys. Have a great rest of the month. Feels weird to say that on the 18th.